Before the talk, I would like to announce something. It is like combinatorial. There will be a conference in 2015 August with the title Combinatorial Constructions in Topology, and the web page is G. Denham. I think it is web page of Professor Graham Denham. So this is the website of this conference. So please look at that. Okay, so now let's come to this talk. So what is the motivation of this work? Right? The motivation is very simple. It comes from my school days ideas. So we know what is complex projective space, and this is the heart of algebraic geometry and toric topology. And I wanted to know more about these spaces. But what I know from the physics class in my school days, that if I want to know more about the particles, I have to divide the particles. So I took that idea. So I have to divide the complex projective spaces. Now how I can divide that? And triangulation is the old technique in mathematics. So I use that technique to divide these complex projective spaces. So this was the motivation. Okay, so let's start with a very simple definition. That is n simplex. These are all positive. These are all points in Rn with positive coordinates, such that sum of coordinates is less equal to 1. Now let's just define that n-dimensional compact torus in Cn, which are like Z1, Z2, Zn, such that moduli of each coordinate is equal to 1, and which is isomorphic to Rn mod that n-dimensional lattice in Rn. Okay, and let V del n equal to the set of all vertices of this n-dimensional simplex. So these are some notations. And L del n is the set of all faces of n-dimensional simplex. Okay. And F delta n equal to the set of all facets, which are codimension 1 faces of del n. And Fi is the facet of n-dimensional simplex which does not contain the vertex Vi. Okay, so up to this is very simple, right? Now we want to define, recalls the definition of triangulation of manifolds. First I have to say what is cell in Rn. A cell is nothing but the convex hull of finitely many points in Rn. So this is my definition. Now it is saying a geometrical cell complex K is a finite collection of cells in some Rn, such that it satisfies two conditions. One condition is if sigma is a face of tau, then and tau is an element of K, then sigma is also an element of K. And if both sigma and tau they belongs to the collection K, then their intersections they also belongs to the collection K, and they are both faces of the intersection is a face of both of them. Okay, so this is the definition. This is my definition of geometrical cell complex. And zero-dimensional simplices are called the vertices of K. Now, if we take a geometrical cell complex K, and if each element in K is a simplex, by simplex means it is a PL homeomorphic to our n-dimensional standard n simplex del n, then we say that cell complex is a simplicial complex. So let's give a very nice example. So this is a simplicial complex with 16 vertices. This is we can see this is a square in R2. Okay. Now if we have given a manifold M and a simplicial complex K. And if we can find a homeomorphism between M and the union of all simplices in K, then we say that K is the triangulation of the manifold M. Okay, this is simple definition, right? Okay. Now, if we identify the antipodal point of this square, which I gave the same picture in the 2 slides before, then we will get a triangulation of 2-dimensional compact torus with 9 vertices. Okay, so this is an example of triangulation. Now let us discuss some known triangulation of CPN. Here Banchoff and Kuhnel in 1983 they constructed a vertex minimum triangulation of CP2 with 9 vertices. By vertex minimum means there does not exist any triangulation with less number of vertices. Okay. Okay, so this is the old result. And around 1991, Ornox and Marin, they gave a lower bound on the number of vertices of a triangulation of CPN. And that number of and that lower bound is 1 plus n plus 1 square by 2 if n is greater or equal to 3. So this is the lower bound on the number of vertices. Okay. Now, another known results about the triangulation of CP3. In 2012, Bakchi and Datta, they constructed a nice triangulation of CP3 with 13 vertices, and then they used the bistellar move to reduce the number of vertices of the triangulation, and they got 18 vertex triangulation of CP3. So this is my result that if n is greater or equal to 4, it was not known any explicit triangulation of CPN. And I showed that there exists a triangulation of CPN with 4 power n plus 1 minus 1 by 3 vertices for all n greater or equal to 1. Yeah, and the number of vertices is too much, but it is very nice triangulation. So this is my results. Now I will discuss the sketch of proof. To construct this triangulation, I used the toric technique. So what is the toric technique? Let us recall that toric technique. I will just recall the construction of CPN by Davis and Januszewicz. So first I consider the standard basis E1 to En of Zn, and let E0 is the sum of this standard basis. So we can define a characteristic function of n-dimensional simplex given by Xi, which sends Fi to Ei. Okay. So this is a 2-dimensional example of characteristic function. And also this is 3-dimensional example of the characteristic function. So using this characteristic function and the polytope, we want to define CPN. So suppose f is a non-trivial face of n simplex. Since it is non-trivial, we can write f as a unique intersection of some k many one-dimensional faces, codimension 1 faces. So given this condition, we can define a submodule ZF of the lattice, n-dimensional lattice Zn, and which is generated by this xi fi1 to xi fi k. Okay, so corresponding to this sublattice, so by our condition, this sublattice is a direct summand of Zn. So given this submodule, we can define a compact torus, which is Tf, which is defined by that ZFR by mod ZF by Tn. So what is ZFR? This is just that we know that ZF, which is so we can define this tensor over Z with real numbers. So this is our ZFR. So this is a subtorus of Tn. So what we notice that given a non-trivial phase F, we can associate a compact subtorus Tf. So Davis-Januszewski gave this construction. So we can identify 2 points t, x and s, y by this relation if x equal to y and s T inverse belongs to Tf, where x belongs to the relative interior of F. And they showed that, Davis and Januszewski, they showed that CPN is equivalently homeomorphic to this quotient space. Okay. So given this quotient space, we can define the orbit map, which is defined by Tx goes to x. So this is very simple argument. Okay, now we will recall the cubical subdivision of n simplex. So this is the cubical subdivision for a two-dimensional simplex, which is triangle. So what is this? The subdivision, we say cubical because we can write this as a union of cubes. First zero-dimensional cube is this one, then one-dimensional cube this one, this one, this one, and the two-dimensional cube is this area and this area and that area. Okay, so this is the subdivision for del 2. Similarly, we can define the cubical subdivision for del 3. Right? Is it okay? Actually, for a general case, we can construct the cubical subdivision for simple polytope. And in the book of Bustavar and Panov, they describe it very nicely. So I used their ideas to construct this cubical subdivision. So using this cubical subdivision, first we can subdivide CPN with this type of subset, which is inverse image under the orbit map of these cubes I sigma, where sigma belongs to a face of n-dimensional simplex. So from this we have another observation that if sigma is a face of tau, then pi inverse I tau is a subset of pi inverse I sigma. Okay. And now what I did, I did that I construct triangulation of all these subsets such that they are subcomplexes. So for example, I construct the triangulation of all pi inverse I sigma such that if sigma is a face of tau, then this pi inverse I tau is a subset of pi inverse I sigma. I will do for CP2 case. Here. So for CP2, what we have, we have this triangle, right? Now we have this cubical subdivision. So this is our orbit map. So what we know, the inverse image of this point is our torus, right? So this is T2. Now what will be the inverse image of this line? That will be, this is inclusion to homeomorphic to D2 cross S1. And what should be the inverse image of this line? This is also homeomorphic to D2 cross S1. And also we have another inclusion. This is also D2 cross S1. And the inverse image of this is just D2 cross D2. So we have this type of diagram, D2 cross. And here is also D2 cross D2. So as I showed in that picture, when I defined the triangulation of manifold, a triangulation of compact two-dimensional torus, I consider that torus, that triangulation with 9 vertices. Then I tried to extend this one. So this is the boundary of this solid torus. So I extend this triangulation to this solid torus with 9 plus 3, that is 12 vertex. So this triangulation, the triangulation of the solid torus contains 12 vertex. This is also 12 vertex. Now what we need? We need that when we will extend this triangulation, we have to notice, we have to be careful when we will take this union, that should be triangulation of S3. Is that okay? Because this union should be S3, because this is the boundary of D2 cross D2. So this union should be S3. So we have to make the triangulation in a nice way so that the union of these two triangulation is the triangulation of S3. This type of construction was given by Banchop and Kuhnel. They used 7 vertex triangulation of T2. And they tried to extend in the similar way. But for higher dimensional cases, they failed. So I used this toric concept to generalize their argument. Is the argument okay? This is very simple, right? Not difficult. But to extend for higher dimension, it is little bit tricky. But what I used two concepts. One is like we have Z3n action on Tn. It is just by rotation around like 120 degree. So that I consider a Z3n equivalent triangulation of Tn, and then I try to extend for other faces. Okay, so this is the idea of proof. Now what type of question we can ask? So now we know the CPN is divided in simplex. The another goal was to triangulate CPN is I want to see the subvarieties which are like toric varieties, in particular smooth projective toric varieties, in terms of this triangulation. So yeah, that is my new project. Yeah, that's all.